In these videos, we're going to talk about the resultant. We're going to use that to compute intersection of curves as well as to eliminate variables and find implicit equation of parametrized curves. To motivate the definition of the resultant, let us try to answer the following question. Do these polynomials have a common zero over C? More generally, how do we tell whether or not two polynomials have a common root? Obviously, trying to compute the roots is not a good idea, since we know that there is no general formula to compute roots of polynomial of higher degree. So how could we tell whether or not two polynomials have a common zero without actually explicitly finding their roots? Let us try to first find a necessary condition. And to do so, we want to think of roots as factors. So suppose that f and g have a common root alpha. This means that x minus alpha must divide both f and g. In other words, gx divided by x minus alpha must be a polynomial of degree strictly less than degree of g. Similarly, fx divided by x minus alpha must be equal to some polynomial of degree strictly less than degree of f. Thus, we immediately see the following necessary condition. If f and g have a common zero, then there must exist non-zero polynomial rx and sx such that f times r is equal to s times g, and the degree of r is strictly less than the degree of g, whereas the degree of s is strictly less than the degree of f. Now we claim that this condition is actually also sufficient. That is, if there do exist such polynomials r and s, then f and g do indeed have a common zero over an algebraically closed field. So let's see why that is. Let's suppose that we can find non-zero polynomials r and s such that the degree of r is strictly less than the degree of g, the degree of s is strictly less than the degree of f, and f times r is equal to s times g as polynomials. Let us try to show that f and g must have a common root. For concreteness, let us just use our examples here. That is, let's assume the degree of g is 7 and the degree of f is 5. Now, why does the existence of polynomials r and s imply that f and g must have a common root? Well, over an algebraically closed field, f would split into linear factors. And since the degree of f is 5, it would split into exactly 5 linear factors, counting multiplicity. Now, since the polynomial ring over a field is a UFD, and these factors are irreducible or equivalently prime elements, each of them must divide either s or g. Now, since the degree of s is less than 5, at most 4 of these can go into s. In other words, at least one of these must be a factor of g. That would correspond to a common root of f and g. Thus we see that f and g have a common zero if and only if there exist polynomials r and s such that the degree of r is strictly less than degree of g, and degree of s is strictly less than degree of f, and f times r is equal to s times g. Okay, so this is indeed a sufficient and necessary condition for two polynomials to have a common zero. But it doesn't seem computationally very useful. We want to actually have an explicit algorithm to tell whether or not two polynomials have a common zero. Thus, our goal in the next video is to translate this statement into something that could be turned into an algorithm.